I don't have a PowerPoint. I have a PowerPoint later, but I'm not going to do it because I just want to. I knew this was Hattie was here and Dingham was here and Greg was here. We're talking about big picture ideas. I really wanted to get down to some detail and make it more of an interactive process. And I picked 3 topics: the teaching of subtraction, multiplication and division. But I want to show you a little bit of, you're laughing, yeah, a little bit of pedagogy on this one and show you where it goes. And I want you to stop me whenever you feel like it. So you think, why should this guy be teaching this stuff? This is primary maths. Well, the reason is, with subtraction, there was a question a couple of years ago and it was something like this: $135 was the price of a bike. And then the kids had supposedly saved up something like $49. How much more money did they need to save? And this was in NAPLAN in year 5 and also in year 7. But this stuff is taught in year 2. And so what do we have to do with this? This is just a plain subtraction with renaming. The area is, how much money do I have to save is a missing part context. And among the grade 5s, 30% got it wrong. And among the grade 7s, 20% got it wrong. But this is something that you might have assumed should have been mastered by about grade 3. So I had that question in mind and I set another question. And this question was, there were 40,000 people at the Broncos game, and at the end of the game 2,368 or something like that departed. How many to watch the second half? And in this instance, what I had was 31% of the cohort got it wrong. But the cohort wasn't grade 4 or 5. The cohort had done 12 years of schooling and 4 years of university and were about to become primary school teachers. And they'd also done 2 maths curriculum courses. So I started asking questions and I realised that at least in some institutions there's a lot of focus on the big picture ideas but not on the detail. So I'm going to spend a bit of detail about the teaching of subtraction. Another reason for that is every year I get my students to go out and find a kid off the street. They get their cousin, their relative, their next door neighbour, something like that, and they do a diagnostic test on them and then they have to remediate it. And for the primaries it's nearly always subtraction. Lots of kids get killed with subtraction. So we'll do subtraction. And now I've got to look at the time. I've got only a couple of minutes. So I had all this material here and I was going to go over it and get you guys to use it, but I think I'll run out of time. So I'm just going to use the counters up the front and you can see me doing it up the front here like this briefly, okay? And we'll see where it goes. So we start with subtraction, and of course we've got a frame like this, and we might have a little story. There were 6 little birdies, or I had 6 little cookies in my hand, and Mummy came away and took away 2, and so now I have 4. So that was 6 to take away 2 is 4. There's another context, and that is I have 6 toys and my brother has 2. How many more does he have? And we'd stick the brothers up and we'd see the difference is 4, and that's compare. Or I am 170 centimetres tall and Michael is 194. How much taller is Michael? Let's compare. And there's another context, and that is missing part. There's a dozen eggs in the milk carton, in the egg carton. some have been eaten, and now there's only 3 left. So for subtraction, there's only 3 contexts the kids got to remember. So back at that original problem, maybe the kids added when they saw the word more. How much more money do I need to save? So when you're teaching, put as often as possible in the primary years, put things in a context, and for subtraction there's only 3. And once the kids identify the context, it's done. And now it's just an algorithm that you have to teach them. And the algorithm can easily be taught with materials. And I'm going to pick a slightly larger number now. So I'm going to get, I hope there's 10 in here. I'm just going to check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this problem is going to be, I have 13 lollies. We'll put it up there. And the dog came in and ate 6. And so it becomes, I have 3 lollies, there's 3 ones. I have 3 ones. Can I take away 6 ones? Can I take away 6 ones? No. So I rename. So I rename one of these 10s. And now how many ones have I got? Well, I've got no 10s, because there's my 10s and there's my 1s, and I've got 13 ones. Can I take away 6 ones? Yes, do it. And so we take them away. 1, 2, 3, 4, 5, 6. And if we don't have our number facts, we count them all out. 1, 2, 3, 4, 5, 6, 7. And the answer is 7. So the algorithm is not built up just by telling them rules. The algorithm is built up with a material proof, and this is the material proof, and it's built up with consistent language. So now we'll get to the problem that confounded my students. And I said I had 40,000 at the Broncos game, and 2,328 departed at half time. How many remain to watch the second half? 0s, 1s, 10s, 1s, 10s, 100s, 1000s, and 10,000s like that. So what they were doing is, I think, trying to rename all of these numbers one at a time, and they had all this writing going up the top there, and they made mistakes. So we'll make that a little bit easier to show the pattern. I have no 1s. Can I take away 4 1s? No. Rename. I have no 10s. Actually, I do have 10s. I have a lot of 10s. How many 10s?
40.
I got 40 10s. If I've got 40 10s and I rename one of them, I'll have 39 10s and 10 1s. So over here, how many 10s have I got? I've got 4,000 of them. If I rename one of them and 10 1s, I can do it like that. And 10 1s take away 8 1s is 2, 9. 10s take away 2 10s is 7. 900s take away 300s is 6. 9,000s take away 2,000s is 7,000s. There's my answer. Now about pedagogy, and when I'm talking to my student teachers, every time I touch the blackboard, I'm explicitly saying exactly what I'm doing with the place value language. Now, you're all experienced teachers, and I don't know what the Victorian system is like, but can you close your eyes, please? Close your eyes. Then put your hands up if that's new. Hands down. Keep your eyes closed. Put your hands up if you're already familiar with that form of renaming and the use of that material. Okay. Hands down. Put your hands up if you're familiar with the use of the bundling sticks on the place value chart to teach number. That's fantastic. Put your hands down. Okay, that's good. Now I've got a bit of an idea. So I didn't really need to do that because most of you had already seen the use of place value material and bundling sticks, and it perhaps only maybe a quarter had seen the shortcut method of renaming. So let's come down to multiplication. We start this in grade 2, and we've got something like this. And
are we going to discuss whether that was an effective method?
Pardon?
Are we going to discuss whether... Are you saying you think that's a good idea?
What's a good
Is that
idea?
what you're saying?
What's a good idea?
Your paddle pop sticks renaming, talking about your place value, and is that what you're advocating?
What do you think?
I think you're saying yes.
Well, when the students are taught other algorithms, for example, mental computations, they might have something like, I don't know, 62 take away 18, and they set it out horizontally, and they take away a 10 from this, and then they get 52, and then they have to take away 8 from this, and then they get 46, something like that. Have I made a mistake there? Anyway, let's do it with an algorithm. 62, take away 18. I've got 2 ones, can I take away 8 ones? No. Rename. I'll rename one of them and I'll have 12 ones. I have 12 ones, can I take away 8 ones? Yes, 4 ones. I have 5 tens, can I take away 1 10? Yes, 5 tens. That process is repetitive, and it's always using the place value language explicitly. And it stops the problem of 62 take away 18, and biggest from littlest is 6. It stops the process. And the horizontal methods tend to be much harder on cognitive load. So it just becomes now a routine. It's like, 1 2 buckle my shoe, but it's a routine that has meaning behind it, and it's very effective.
Okay.
I think it's very effective.
I hear what you're saying.
Yeah.
I don't understand the correlation between you telling me this is very effective, but making an introduction where 30% of the children got it wrong when it's a year 2 operation.
They weren't children. They were university students who got it wrong.
Who've been through the whole education.
That's correct. That is correct.
I would state that partly why they have got it wrong is that early on we used a different takeaway method, which I continue to use myself.
Yeah.
However, there is a confusion between the old method and the new method, and it has substantially affected adults with subtraction. Because how you do, I do give to the top and give to the bottom. That's my old-fashioned method. And what you did then, for people who aren't very good at maths, you race through from very small unit to a very large unit.
Oh.
So 40,000, deciding that was, even when you put up the units 10, you went quickly and you made a little bit of a mistake there. I think for kids with the mathematical issues, the place value is really, really important in understanding the subtraction.
Yeah,
so
you're absolutely...
doing a lot of place value before the subtraction.
I know just for me, I really struggled with maths in primary school. I'm at university at the moment. We've learnt this way. I get it. Because I'm understanding the place values, whereas when I was taught at school, it was this is how you do it, but you don't understand why you do it that way. So for me, it's helped me understand why that makes sense.
That's the point of this though, isn't it? It emphasises place value.
Yes. Yeah.
So, it's supposed to emphasise place value. I actually started with this one, and after this one, I go and these out with my base 10 material, and I do the process of renaming, methodically until they're sick of it, and they understand place value with these materials. These are base 10s, and these are 100 blocks here like that. And I stick with this for grade 1 and grade 2 until they've got place value. But once they've got place value, then I can go to the abstraction and get rid of it. How long I take with the materials depends upon the kid. But when remediating grade 7 kids who don't understand subtraction, I have to go back to this almost always, because if I go to an algorithm without an understanding of place value and the base 10 system, they don't get it. In fact, they just have a rule. And the fact that you and a lot of other people can do it with the rule is you memorize the rule. But it's hard to remember lots of different rules. And what I'm going to show you with this is I use the same language with fractions and expressions as well, and I use the same rules basically, and we'll get on to multiplication. But I think it's important that we interact. Yes?
I was just going to say really quickly, I do prep to 6 maths intervention support, and I agree that it is extremely important. I get the 5s and 6s come in who are trying to do the abstract method of subtraction, and it's not until you sit there with the place value chart and you're doing the renaming with them with concrete materials, and the penny drops and they say, that's what that one is, that's what
right.
that means.
That's right. Well, when you closed your eyes, nearly everybody put up their hand that they were familiar with using these materials. And so I thought, okay, I didn't need to teach that. You guys are sweet on that. We'll go for it. But that's a big difference to other parts of Australia. And by the way, about 10% of Victorians are in the advanced mathematics with TIMS testing, and only about 5 or 6% of Queenslanders are in there. But overall, we're way down compared with our international competitors. Yes?
I'd just like to comment that in general, in primary schools, in the lower levels, grade 1, 2, they're familiar with using concrete materials like paddle-pop sticks.
Yeah.
And in the upper grades, 5, 6, certainly 7, no.
Well, it depends on the school, and if they've used them in grade 1, 2 and 3, they don't need them in 4, 5 and 6. But if they haven't used them in grade 1, 2 and 3, you've got to bring them back in grade 7 and 8.
You use them in grade 1, 2 or 3 like this with your base 10 to do your positive numbers, and then you use them in 4, 5 and 6 to do your decimal numbers and your thousands.
Yes, well you can.
Suddenly.
Yes, you can. You can use that as a 1, and that becomes...
You can use your thousands.
And so that can become a 1.
Yeah.
And this can become a 10, 1/10, and this can become 100ths, and the other one is 1,000ths. Yes, you can. But in terms of the whole numbers, hopefully you don't have to, but you will have to if they don't understand it. You've got to go right back to the beginning. So I'll move on now. So we're okay on subtraction? We sweet?
We're all good. I just wanted to make sure I knew where you were going.
Yeah. So now I'm going back to grade 2, and we're doing repeated addition. And we can 3 and 3, and we see that this is 12. And then we say, well, that's that's an array. I can make an area model out of this like this. And now I've got a piece of carpet, and it's 3 meters and 4 meters, and we can count them all out, and that's 12. And then I can start building my algorithm on my, and by the way, at this point in time, now I can start memorizing all of the number facts, the multiplication facts up to 100, and there's strategies to do that, but we won't go through them now. And so now I can do something like I've got 3 there, and another 3 there, and another 3 there, and another 3 there, like this, and I've got 1, 2, 3, 6, 9, 12. So I've got the same thing. I've got 4 lots of 3, and I've counted them as 12. Well, I'm going to rename that as 10, that's 6, 9, 10, put a rubber band around it, and I've built my algorithm where I've got 3 multiplied by 4 is equal to 12. I've physically done it. And I keep doing that, and I move over. The next step is to go over to these things. But this time, I'm going to draw this because I'm aware of the time. So rather than putting them out and having me drop all the things all over the place, I'll just sketch what we've got here. Just say I'm doing an algorithm like 14. I have 3 dump trucks, and that can carry 14 tons each. How many tons altogether? So when I put my materials out, that will be 10s and 1s, 110 and 1, 2, 3, 4, 110 and 1, 2, 3, 4, 110 and 1, 2, 3, 4, like this. And so that's 3 by 4 is 12. Rename. Rename. I'll rename one of the 10s. I'll take that 8, and that 2. So when I draw it now, it's going to be 10s and 1s. There's that renamed 10. That's those ones there. And then I've got 1, 2, 3, like this. I can see the answer in front of me now. The answer is 2 and 4 10s. The answer is 42. So when I build the algorithm now, I write it symbolically. This is going to be 14 multiplied by 3. 14 multiplied by 3 is 2 1s, rename as 1 10. 3 multiplied by 1 10 is 3 10s, and 1 10 is 4 10s is 42. So there's an exact correspondence now between the materials and the algorithm. And I do that with these little bundling sticks, and then I go and do it with these little ones up to here. So I'm multiplying 128 multiplied by 4 and things like that till the kids get sick of it. And then I think, well, let's make another link because we've got a nice area model there. What about if we go 14 multiplied by 3, but this time we'll do it in an area model, and we'll do that as 10 and 4 and 3, and 4 by 3 is 12, and 3 by 10 is equal to 30. So the total area in there is going to be 30, and 12 is 42. It's mirroring what's happening with the algorithm. 3 by 4 is 12, that's what we got there, that 12. Rename is 110. 3 by 110 is 30, and 110 is 42, and that's a 3 by 110 is 30. So there's a good correlation there. Got to find a pen that's not so big. Here we go. So I can go a little bit further with looking at the relationship between those two algorithms. Say we do something like 13 multiplied by 14. There were 14 dump trucks and they could carry 13 tons each. And so this becomes 4 multiplied by 3 is 12, rename as 2 10s. And 4 multiplied by 1 10 is 4 10s. And 1 10 is 5 10s. And 10 multiplied by 3 is 30. And 10, pardon?
Lost your visual. You're too far over.
Is equal to 30. And then 10 by 10 is equal to 100. So add all the parts to 8 10s, 182. The exact algorithm, 10 and 3 and 10 and 4. 4 by 3 is 12. 4 by 110 is 4 10s, and which is 40. So that's my 52. And 10 by 3 is 30. So that's my 30, 3 10s, and 10 by 10 is 100. So there's my 100, add the parts, same thing. 130 and 40, 170 and 12 is 182. So there's the structure, and it works for multiplying very large numbers as well. And people say, well, why bother with this vertical algorithm? Well, it's good. It's a very useful algorithm because when I get something like 2x add 3 and x add 4, and I have to multiply these, and we do this in grade 10, 4 by 3 is 12, and 4 by 2x is equal to 8x, and 8 by 3 is x by 3 is equal to 3x, and x by 2x is equal to 2x squared, and all the integers are positive, all the signs are positive. Collect the parts 12, 13x, and 2x squared. I've just used the same algorithm that I taught in year 3 with year 10s, and now I use this method, and so we'll say 2x add 3. We'll make that the box there like this, and we'll make this one, the length is going to be x add 4, and we'll multiply. 4 by 3 is 12, yeah, we got that. And 4 by 2x is 8x, yes, we've got that. And x by 3 is 3x, yeah, we got that. And x by 2x is equal to 2x squared. And we collect the parts, 2x squared, x, 8x and 3x, they're the same. I can add those two expressions, is equal to, what did I say? Where'd I get this? 11. You didn't pick me up. You didn't pick me up. Is equal to 11x add 12. And I can do larger ones. There's 3 by 3s as well. So this algorithm comes from there, and this representation is used down there. And this representation is what I'm going to use when I start completing the square in grade 10. I can derive the quadratic formula by using this kind of thinking. I just have to slot in A, B's and C's. Like if I've got ax squared add bx add c is equal to 0. If they understand this, I can build quite quickly at the derivation of the quadratic formula. So that's just, I'm showing you this because it's an example of the hierarchical nature of mathematics and the importance of learning this detail and these algorithms and mastering them on the way through. Yes?
So then doesn't that give weight to the argument of not introducing vertical algorithms early on in the primary school? If you were to introduce your grid aerial system for our 2-digit addition, then you're giving those young children the same depth of understanding before you even move to renaming that you're giving your year 11 students with their algebraic understanding.
I'm not sure if I got the question correct, but when I teach addition, we do it vertically. I never teach horizontally.
No,
But the same with multiplication.
Your aerial view.
At the area model, these two models here,
Yeah.
I can teach this easily because I can get out my materials. I only have to generalize when I start multiplying by 10 because they get too much materials on the board. But I can certainly develop my algorithm with materials up to 45 multiplied by 3 or 4 or something like that, and then I generalize and don't use materials. So I think I want to teach this from the get-go, and as soon as they start to get this, I'll reinforce it with this and make the connection.
But
And
I'm
some
thinking
kids-
about going further backwards, taking your argument. I think what I'm doing is taking your argument back to the beginning and saying, in the beginning, would you not take that same argument before you make your generalisations?
Oh, okay.
When you're working with abstract.
All right. So
It's basically a
you want to
digit
stick with the area
abstract.
model early.
Yeah.
Yeah, fine. Do a PhD on it. If it works, sweet. And you'll find that some kids I do this with my adults and kids, and some like the algorithm and some like the area model.
Yeah.
Yes.
And often it's the boys who like the area model, and sometimes it's the girls who like the algorithm.
Just
Now,
one
I don't know
argument
why.
is-
It doesn't matter,
I think more children fall off maths before they need to because then their thinking has become too generalised and too narrow too soon.
Yeah.
So the broader we keep it, the longer, the less children we lose.
Well, I would stick with, for multiplication, I would stick with the vertical algorithm, the area model, and there's one other method called lattice. But you don't want to give them too many different methods, otherwise they get somewhere like, which method do I use? And we've got this thing called division, which, how are we going for time?
Perfect. Got
We're
10
not.
minutes.
We haven't done any fractions. We're going terrible. So, okay, let's do division quickly and we'll go, okay? So, just say, I'm going to do this with a pen and paper because I can actually go a bit quicker than putting the materials out, if you don't mind, although you would do it with materials with the kids. Just say I've got some lollies, and I've got 12 lollies to be shared amongst 3 people, Julie, Susie, Lucy. So this is 12 divided by 3. And the kids have to learn that sometimes the silly textbooks write it like this, 12 divided by 3. And then when they get up a bit further, they go 12 divided by 3. But it's all the same. It's all 12 divided by 3. It's just bad luck that they write it in different ways. So we've got 12 of them. Julie, Susie, Lucy, Julie, Susie, Lucy, Julie, Susie, Lucy, Julie, Susie, Lucy. 12 divided by 3 is 4. And they'll soon tell you, why didn't you just go, what number multiplied by 3 gives you 12? It's 4. Okay, what about this? If it's 13, well, there's the remainder 1. That one wasn't shared. So it became, so there was 4. If this was 13, there would be 4 in each share and 1 was unshared. And if we were a bit more advanced, we would say 13 divided by 3, there was 4 in each share, and this is a third of a share. Because a whole, well, is this a third of a share? This is equal to 4 multiplied by 3 is 12. Do the takeaway is 1. This is 1/3. So this is what's left over, a third. So let's now have a look at that algorithm away from the material, those materials, and use our base zeros and tens. I've got a 10 and 1, 2, 3. I have 1 10. Can 1 10 be shared amongst 3? No. I get it. You guys get the ones. It's got to be renamed. So we've got 13 divided by 4. No. Can 13 ones be shared amongst 3? Yes. How many in each share? Oh, these are 4 people here. How did I get that?
Yeah, you changed it.
Have I changed it? Okay, all right, we'll do it this way. 13 divided by 3. Okay, how many in each share?
4.
Okay, what number multiplied by 3 gives me 13, a little less? 4. How many was shared? 4 by 3 is 12. And how many remain to be shared? Do the takeaway 1, remainder 1. And if I had it like this, I would have, the second picture would have been 10s, 1s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And the next picture would have been the shares. 1 for you, 1 for you, 1 for you, 1 amongst 3 people. 1 for you, 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 1 for you. So that's 12 was shared there, and 1 didn't get shared, okay? So later I gave this problem to some students, and this one was convert 3/8 to a decimal. So what does this mean? This means it's 3 divided by 8, or this means that it's 3 divided by 8. Well, that's the most familiar to me from grade 3. So I'm going to go 3 divided by 8. These are ones, tenths, hundreds and thousands. I have 3 ones. Can it be shared amongst 8? No. Rename. I have 30 tenths. Can that be shared amongst 8? Yes. How many in each share? 3. How many were shared? 3 by 8 is 24 tenths. How many remain to be shared? Do the takeaway. 6 tenths. Can I share 6 tenths amongst 8? No. Rename. Can I share 60 hundredths? What number multiplied by 8 gives me 60 or a little less? 7. How many were shared? 56. Do the takeaway. How many remain to be shared? There are 4 hundredths. Can I share 4 hundredths amongst 8? No. Rename. Can I share 40 thousandths? Yes. How many each share? 5. How many were shared? 40. How many remain to be shared? None. There it is as a decimal. Now, when I ask students to convert this to a decimal, then I'm looking at a success rate of 10% or thereabouts after 12 years of schooling. And so my point is, if I walk into a grade 5 class and I've taught division, and then I go into grade 6 class and I teach division again, if I'm using this consistent language, if I can't get 80 or 90% of them to understand the division algorithm, there's something wrong with me. And yet the whole school system, they're all going through, and not all, but so many are going through and not being able to do a simple algorithm like this because they've been taught other algorithms or been taught other stuff without meaning. The repetition of word that's meaningful, the use of materials, it just reinforces a consistent approach to teaching throughout the school. It just shouldn't be happening in my view. Now I'm quickly going to touch on fractions, because one of the other questions that came up in NAPLAN that the kids did dismally in was 0.2, this is a silicon chip, 0.2 centimetres by 0.3 centimetres, what's the total area? And you can guess it, they all said 0.3 centimetres squared, or 0.6 centimetres squared, or they might have forgotten the centimetres squared, but they get this. So let's have a look and see what this is, and go back to our model. This is 2/10 multiplied by 3/10. So I'm going to draw up my 1, as this lady pointed out earlier, and this is not 100 anymore, this is going to be 1. And I'm going to cut it up. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 cuts is going to give me the tenths. And this can be my 2/10 there. And then I'll do the cuts this way. 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is there's my 2/10 there, and my 3/10 there. And my 2/10 and my 3/10, this is the size of my chip. Colour it in. And what is this? 1, 2, 3, 4, 5, 6 out of how many altogether in there? Out of 100. In other words, they'll soon generalise. This is 6 100ths, which is equal to 0.06, because they're the tenths and they're the hundreds. See how the area model's coming out? Now, that took us 2.5 minutes to do, and give me a couple of lessons, I can get mastery with the grade 6s and 7 kids on the multiplication of fractions decimals. I'll never make a mistake, because most of them, and you revise it every now and then, and not going to have an issue with it. It's the same. I believe you won't. I'd love it, someone who can test me, but I think that we can do a lot better. And I've got about 2 minutes. So I'm just going to have a quick look at the division algorithm with fractions, if you like. You happy with that? Yes. Okay. So, good. When we had those things, we said, we're going to share. I've got 12 bananas and there's 3 kids. How many in each share? How many bananas do they get? And you told me 4. But this time, I'm going to say I've got 12 bananas, but each share is 3. How many kids get a share? And you'll go, oh, it's the same. It's going to be 4 kids get a share. Or I'll say I've got 13 bananas, each share is 3. How many shares? And then you count them all up, 4, and there's 1 remaining. We're going to use the same logic. Just say we've got 2 divided by a half. Let's draw it. 1, 2, and the share is a half. There's a half there, and a half there, and a half there, and a half. The answer is 4. Just say I've got 1, 2, 3 cakes, and we can have this one is 3, and each share divided by, I don't know, what do you want to make it? 3/4? Each share is 3/4. So let's do this. 1, 1, 1. That's 1 share. 2, 2. That's the second share. 3, 3, 3. That's the 4th share. A 3rd share, and here's the 4th share. 4, 4, 4. There is equal to 4 shares in there. Now we keep doing these, and eventually the kids are going to see a shortcut, and they'll tell you, and they say, look, we're sick of drawing up our cakes and cutting them up because it's too tedious. So, well, what are you going to do? So what we're going to do is we're going to say this is 3/1 divided by 3/4, which is the same as 3/1 multiplied by 4/3, which is equal to 12 divided by 3, which is 4, or if they've done factorisation, they'll see this as 3 multiplied by 4 and 3 multiplied by 1. 3 divided by 3 is 1, the answer is 4. So, okay, what you did is you inverted the division to a multiplication. It's a reciprocal operation, and you did the reciprocal of the number. But does that work for everything? And they can say, well, let's try it. Let's get, say, 3 divided by 2/3. So what would that look like in your algorithm? That would be 3 over 1 multiplied by 3 over 2, because that's a reciprocal, which is 9 over 2, which is equal to 4.5. And I have to teach that by drawing it out. That's what you think it's going to be. Let's check it. 1, 2, 3, and each one is going to be 2/3, so I'll make it into thirds. That's 1, that's 2, this is 3, this is 4. Right, 4, 4, 4. And, we got 1/3. We got 1/3. How come it's wrong? How come it's wrong? And the answer is supposed to be 1/2. And so you have this argument, you say, look, don't complain, you got 1/3, but shut up, you got half a share. You got half a share. What do you mean? Stop whinging about you only getting 1/3 of the cake, you got half a share. Now, do you follow my logic? Because this person got 2 bits and you only got 1 bit, you got 1 out of 2, you got half a share. So now I build my division of fractions algorithms. And so my point about all this is a bit of detail here. And we haven't done fraction addition, we haven't done fraction subtraction, haven't done lots of stuff, but almost anything that you want to teach in primary all the way up to calculus, you can use materials, you can use logic, and you can use models. And it makes a lot of sense when you do so. And when you use that sort of approach with things, then the kids don't have to memorize rules, they understand the schema of things, they're much less likely to forget. So that's what I'm about. Now, by the way, I got to put in a commercial plug. I built these DVDs, and I've got this guide putting them online from Vimeo. I'll put it up on Monday. But all of my teaching from grade prep through to grade 9, you can have for the price of 2 cups of coffee if you can work out the technology of Vimeo, and a 500-page book. It's at budgetfeatures.com. But anyway, any questions on that before we go and have a cup of tea? Can you close your eyes, please? If you've got no questions, close your eyes. This is me getting feedback. You, lady, close your eyes. Just because you're older than me doesn't mean you can have it. Eyes open. Close your eyes. Was there anything? Hands up if there was not much of you in that. A couple of people. Good. Okay. Right. That's all I needed to know. See you later.